This planet breaks every rule we know. Not in a small way. Not in a we need to tweak our calculations kind of way. I mean, it shatters the fundamental laws of planetary formation that we've built over decades of research. When astronomers first looked at the data, they thought their instruments were broken. They ran the numbers again and again. They called in other teams to verify. Everyone got the same result. The planet is real. And according to everything we understand about how worlds form in this universe, it shouldn't be there. I've spent years studying the cosmos. I've seen things that challenge human imagination. Neutron stars spinning faster than your kitchen blender. Black holes devouring entire solar systems. Galaxies colliding in slow-motion dances that take millions of years. But nothing prepared me for what I'm about to share with you tonight, because this discovery doesn't just challenge what we know. It suggests that maybe we don't know anything at all. Let me take you back to the beginning. When you look up at the night sky, what do you see? Points of light. Thousands of them if you're lucky enough to be away from the cities. Millions if you're in a truly dark place. Each one of those points is a sun. And around many of those suns, there are worlds. Rocky worlds like Earth. Gas giants like Jupiter. Ice worlds. Lava worlds. Diamond worlds. The universe has no shortage of imagination when it comes to creating planets. But here's the thing most people don't realize. We don't just find planets randomly. We understand how they're supposed to form. It's like baking a cake. You need specific ingredients in specific amounts. Too little flour, your cake collapses. Too much sugar, it burns. The same is true for planets. A planet forms from the leftover material around a young star. After the star ignites and begins fusing hydrogen in its core, there's still a disk of gas and dust swirling around it. We call this a protoplanetary disk. Think of it like a cosmic pizza dough, spinning and flattening out over millions of years. Within this disk, small particles of dust and ice start sticking together. They collide gently, bonding through weak electrostatic forces. Over time, these clumps grow larger. Pebbles become boulders. Boulders become mountain-sized chunks we call planetesimals. And eventually, if there's enough material and enough time, these planetesimals merge into full-fledged planets. The key word here is enough. The size of the protoplanetary disk depends directly on the mass of the star. A massive star like our Sun has a proportionally massive disk. More material to work with. More ingredients for the cosmic recipe. A star that's half the mass of the Sun has roughly half the material. A star that's 1/10 the mass of the Sun has far, far less. This is basic physics. Conservation of mass. You cannot create something from nothing. You cannot bake a 10-layer cake with enough ingredients for a cupcake. And this is where our story gets strange. In December 2023, a team of researchers at Penn State University announced a discovery that made the astronomical community collectively scratch their heads. They had found a planet orbiting a star called LHS 3154, located about 51 light-years from Earth in the constellation Octans. 51 light-years sounds far. And it is. Light itself, traveling at 299,792 kilometers per second, takes 51 years to make the journey. But in cosmic terms, this is our neighborhood. This is close enough that we can study it in remarkable detail. LHS 3154 is what we call an ultracool red dwarf star. These are the runts of the stellar litter. Small, dim, cool by stellar standards, though still thousands of degrees at the surface. Our Sun is classified as a G-type main sequence star. LHS 3154 is an M-type dwarf, the smallest and most common type of star in the galaxy. How small? LHS 3154 is about 9 times less massive than our Sun. Imagine taking our Sun and shrinking it down to just over 11% of its current mass. That's LHS 3154, a dim red ember compared to our blazing yellow furnace. Now, here's where things get interesting. Orbiting this tiny star is a planet. The researchers designated it LHS 3154b. When they first detected its presence, they expected something small. Maybe an Earth-sized world. Maybe something a bit bigger like a super-Earth. That's what the physics should allow. But LHS 3154b is not small. It's massive. At least 13 times the mass of Earth. That puts it firmly in the category of subneptune or mini-Neptune class planets. It's a giant. Not as big as Jupiter or Saturn, but far, far larger than anything that has any right to exist around a star this small. Let me put this in perspective. The mass ratio between Earth and the Sun is roughly 1 to 333,000. For every unit of mass Earth has, the Sun has 333,000 units. This ratio makes sense given the protoplanetary disk our Sun would have had. The mass ratio between LHS 3154b and its star is about 100 times higher than the Earth-Sun ratio. 100 times. That means this planet is, proportionally speaking, 100 times more massive relative to its star than Earth is to the Sun. According to our models, the protoplanetary disk around LHS 3154 should have contained about 10 times less material than the disk around our Sun. The maximum planet it could produce, based on everything we understand about planetary formation, should have been around 3 to 4 Earth masses. Maybe 5 if conditions were absolutely perfect. LHS 3154b is 13 Earth masses. This is not a small discrepancy. This is not a rounding error. This planet is at least 3 to 4 times more massive than the maximum possible planet that should exist in this system. It's like walking into a kitchen where someone had a single egg, a cup of flour, and a tablespoon of butter and finding a 5-tier wedding cake. The ingredients simply don't add up. Dr. Suvrth Mahadevan, the lead author of the discovery paper and a professor of astronomy and astrophysics at Penn State, put it bluntly. The planet-forming disk around the low-mass star LHS 3154 is not expected to have enough solid mass to make this planet, he said in the official announcement. But it's out there. So now we have to think about how it got there. This is what I love about science. It's not about having all the answers. It's about being honest when the answers we have don't work anymore. For decades, we've been confident in our understanding of planetary formation. The core accretion model has successfully explained the architecture of our own solar system and countless others we've discovered around distant stars. The gas giants formed in the outer reaches where ice could survive, accumulating massive cores that then gravitationally captured huge amounts of hydrogen and helium. The rocky planets formed in the inner regions, where only metals and silicates could condense from the hot primordial disk. It's a beautiful, elegant theory, and until now it's worked remarkably well. But LHS 3154b throws a wrench into the machinery. It forces us to ask uncomfortable questions. Did the protoplanetary disk around this star somehow contain far more material than our models predict? Was there some exotic mechanism of planet formation at work that we haven't considered? Or is there something fundamentally wrong with our understanding of how worlds come to be? Let's explore each possibility. The first option is the most conservative. Maybe our estimates of protoplanetary disk masses around small stars are wrong. Perhaps ultracool red dwarfs can have disks that are far more massive than their stellar mass would suggest. This would require revising our understanding of star formation itself, since the disk is essentially the leftover material from the cloud that collapsed to form the star. But nature has surprised us before. Observations from facilities like the Atacama Large Millimeter Array, or ALMA, have given us unprecedented views of protoplanetary disks around young stars. In most cases, the disk masses scale with stellar mass as expected. But there are outliers. Some small stars do seem to have surprisingly massive disks. If LHS 3154 was one of these outliers, it might explain how LHS 3154b came to be. The problem with this explanation is the degree of the outlier we need. We're not talking about a disk that's 20% more massive than expected, or even twice as massive. We need a disk that's potentially 3 to 5 times more massive than any model would predict. That's a significant stretch. The second option is more exotic. What if the planet didn't form through core accretion at all? What if it formed through a different mechanism entirely? There's another theory of giant planet formation called disk instability. In this model, instead of slowly building up from small particles, the planet forms rapidly when a region of the protoplanetary disk becomes gravitationally unstable and collapses directly into a planet-sized object. It's a bit like the way stars form, just on a smaller scale. Disk instability works best in massive disks around large stars. It requires a lot of material concentrated in a small area. At first glance, this seems like exactly the wrong explanation for LHS 3154b. How could disk instability work in a system with so little material? But some theorists have proposed modifications to the standard disk instability model that might work in certain conditions. Maybe the disk around LHS 3154 was unusually cold, allowing material to concentrate more easily. Maybe there were specific gravitational perturbations that triggered a local collapse. These scenarios are speculative, but they're not impossible. The third option is perhaps the most unsettling. What if LHS 3154b didn't form in this system at all? Planet capture is a known phenomenon. When stars pass close to each other, gravitational interactions can strip planets from one system and deposit them in another. This cosmic theft on a grand scale. Could LHS 3154b have been born around a larger star and then captured by LHS 3154 during a close encounter? This explanation is appealing because it neatly sidesteps the mass problem. If the planet formed elsewhere, it doesn't matter that LHS 3154's disk couldn't have produced it. But captured planets should show certain telltale signs. Their orbits tend to be eccentric, tilted, or retrograde. From what we can tell, LHS 3154b's orbit is fairly circular and well-aligned. This doesn't rule out capture, but it makes it less likely. There's also a numbers problem. Planet capture events are rare. For LHS 3154 to have captured such a massive planet requires a remarkable coincidence. And in science, when an explanation requires too many coincidences, it starts to feel less like an explanation and more like an excuse. So where does that leave us? Honestly, in a state of beautiful confusion. LHS 3154b shouldn't exist. Every theory we have says it shouldn't be there. And yet, night after night, as LHS 3154 traces its path across the southern sky, that impossible planet is right there with it. Orbiting. Real. Undeniable. This is what keeps me up at night. Not the fear of the unknown, but the thrill of it. Every time we think we've figured out the universe, it hands us something that makes us start over. And starting over means learning, growing, getting closer to the truth. But I want to take you deeper, because LHS 3154b isn't the only impossible planet out there. In June 2023, just a few months before the LHS 3154b announcement, astronomers revealed another cosmic impossibility, a planet that survived its own death. The star is called Baekdu, designated 8 Ursae Minoris in the old catalog system. It's located about 530 light-years away in the constellation Ursa Minor, near the famous North Star. Baekdu is a red giant, a star that has left its main sequence phase and swelled to enormous size as it burns through the last of its nuclear fuel. Orbiting Baekdu is a planet named Hala. It's a gas giant, roughly 1.6 times the mass of Jupiter, completing one orbit every 93 days at a distance of about half an astronomical unit from its star. Here's the problem. Red giant stars are big. Really big. When our own sun reaches this phase of its life about 5 billion years from now, it will expand to roughly 100 times its current diameter. Its outer layers will extend past the orbit of Mercury, past Venus, possibly past Earth itself. When astronomers modeled the history of Baekdu, they calculated that at its maximum expansion, the star should have been about 1.5 astronomical units in radius. That means its surface would have extended well beyond Hala's current orbit. In other words, the planet should have been swallowed. It should have spiraled inward as it plowed through the star's outer layers, losing energy to friction and drag. It should have been consumed, vaporized, destroyed. There should be nothing left. But Hala is still there. How? That's the billion-dollar question. The research team, led by Mark Hahn from the University of Hawaii, proposed several possible explanations. One involves the merger of two smaller stars. If Baekdu was originally a binary star system, the merger of the two stars might have prevented either one from expanding to a full red giant size. This could have allowed Hala to survive in a larger orbit that later decayed to its current position. Another possibility is that Hala didn't exist until after Baekdu became a red giant. If the stellar merger scenario is true, the collision could have thrown off enough material to form a new planet from the debris. Hala might be a second-generation world, born from the ashes of stellar death. Both explanations are extraordinary. Both require conditions and events that push the boundaries of our models. And both leave us with more questions than answers. What I find most fascinating about Hala is what it represents. This is a planet that, according to everything we know, should be dead. It should have been erased from existence billions of years ago. And yet it persists. There's something almost defiant about that. Something that speaks to the stubbornness of existence itself. The universe seems to want things to survive, even when the odds are stacked impossibly against them. And then there's WASP-17b. WASP-17b was discovered in 2009 by the Super-WASP Planetary Transit Survey. It orbits a star about 1,000 light-years away in the constellation Scorpius. When astronomers first analyzed this world, they found something bizarre. WASP-17b is huge. It's about twice the diameter of Jupiter. But here's the thing. It's only about half Jupiter's mass. Maybe less. Do the math. Double the size, half the mass. That means the density of WASP-17b is incredibly low. It's one of the puffiest, most inflated planets ever discovered. If you could somehow find an ocean big enough, this planet would float. For years, astronomers struggled to explain how WASP-17b got so bloated. Hot Jupiters, gas giants that orbit close to their stars, are known to be somewhat inflated due to the intense heating they receive. But WASP-17b is more inflated than any standard model can explain. In 2024, observations from the James Webb Space Telescope revealed a potential clue. WASP-17b's atmosphere contains quartz crystals. Tiny, silica-based particles suspended high in the planet's cloud layers, glinting in the light of its star. Quartz, on a gas giant, in the form of atmospheric aerosols. This was the first time such crystals had been detected in an exoplanet's atmosphere. The finding suggests that exotic atmospheric chemistry might play a role in inflating these worlds, but the exact mechanism remains unclear. WASP-17b also has another strange property. Its orbit is retrograde. While most planets orbit in the same direction their star spins, WASP-17b goes the opposite way. This suggests a violent past, perhaps a near collision with another massive body that flipped its orbit. But we're still not sure. The more we look, the more impossible planets we find. Consider TOI 849b. announced in 2020. This world orbits a sun-like star about 730 light-years away. It's roughly 40 Earth masses, putting it in the range of Neptune or small gas giants. But TOI 849b has almost no atmosphere. This is strange because planets this massive should easily hold onto thick gaseous envelopes. Gravity should ensure it. And yet TOI 849b is essentially a naked core, a world that looks like the exposed heart of a gas giant that somehow lost its outer layers. Did it form close to its star, where intense radiation stripped away its atmosphere before it could fully develop? Or did it start as a complete gas giant and something catastrophic blasted its atmosphere into space? Both scenarios seem extreme. Both require events that should be rare in the extreme. And yet, here it is. Then there's Gliese 436b, about 33 light-years from Earth. It's a Neptune-sized world orbiting so close to its star that its surface temperature exceeds 400 degrees Celsius. At these temperatures, water should exist only as superheated steam. But Gliese 436b is covered in ice. Not regular ice, obviously. This is Ice 7, a crystalline form of water that only exists under immense pressure. The gravity of Gliese 436b is so intense that despite the scorching temperatures, water is compressed into solid ice that refuses to melt. Burning ice, an oxymoron made real through the strange physics of extreme conditions. I could keep going. I could tell you about KLT9b, a world so hot that it's hotter than most stars. Its dayside temperature reaches 4,600 Kelvin, hot enough to vaporize iron, titanium, and other metals in its atmosphere. Molecules on this planet are torn apart by heat, only to recombine on the slightly cooler night side before being destroyed again in an endless cycle of chemical violence. I could tell you about Trace 2b, the darkest planet ever found, reflecting less than 1% of the light that hits it. Darker than coal. Darker than black acrylic paint. A world that absorbs almost all the energy it receives, for reasons we still don't fully understand. I could tell you about HD 189733b, where it rains glass sideways. Silicate particles in the upper atmosphere condense into tiny glass shards that are then whipped around the planet by 5,400-mile-per-hour winds. Each of these worlds challenges our assumptions. Each one forces us to reconsider what's possible. But let's return to LHS 3154b, because I think this discovery is particularly important. The other planets I mentioned are weird. They have extreme properties, unusual compositions, bizarre behaviors. But they don't fundamentally challenge how planets form. They're strange, but they're still within the realm of possibility. LHS 3154b is different. This planet shouldn't exist according to the most basic principles of planetary formation. It's not just unusual, it's impossible. And the fact that it's there anyway tells us something profound about the limits of our knowledge. Consider this. We've been studying exoplanets seriously since 1992, when the first confirmed planets outside our solar system were found orbiting a pulsar. Since then, we've discovered over 5,500 confirmed exoplanets. 5,500 worlds beyond our own. That sounds like a lot, and it is. But our galaxy alone contains an estimated 100 to 400 billion stars. If most of those stars have at least one planet and many have multiple, then the galaxy contains hundreds of billions of planets. Maybe trillions. We've surveyed a tiny fraction of a percent. A sample size so small that it's like trying to understand all the oceans of Earth by studying a single cup of seawater. And already, within that minuscule sample, we found planets that break our models. What else is out there waiting to be discovered? What other impossibilities are orbiting distant suns, waiting for us to notice them? This is why LHS 3154b keeps me awake at 3 a.m. It's not just about this one planet. It's about what this planet implies. If our formation models can be this wrong about a system just 51 light-years away, how wrong might they be about everything else? Maybe planets form more easily than we thought. Maybe the ingredients for world-building are more abundant than our conservative estimates suggest. Maybe the universe is more fertile, more generous, more creative in its architecture than we ever imagined. Or maybe there are mechanisms at play that we haven't considered at all. Forces and processes and cosmic coincidences that combine to produce worlds where they have no right to exist. Either way, we need new ideas. The researchers behind the LHS 3154b discovery have been careful to emphasize that this finding should motivate new observations, not new conclusions. We need to study more ultra-cool dwarf stars. We need to find more planets around them. We need data, not speculation. But responsible scientists are also beginning to ask whether our models need to be rebuilt from the ground up. Not tweaked, not adjusted, rebuilt. That's a scary prospect. It means admitting that decades of work might be based on incomplete assumptions. It means accepting that the textbooks need to be rewritten. It means starting over in some ways from scratch. But it's also thrilling, because starting over means discovery. It means the chance to be surprised. It means the universe still has secrets to reveal, and we're still humble enough to be taught. I think about the astronomers who first detected LHS 3154b. They used an instrument called the Habitable Zone Planet Finder, or HPF, mounted on the Hobby-Eberly telescope at McDonald Observatory in Texas. The HPF is specifically designed to detect planets around cool, red dwarf stars by looking for the tiny wobbles these planets induce in their hosts. The wobble method, formerly called radial velocity detection, works because planets don't just orbit stars. Stars and planets orbit their common center of mass. When a planet pulls on its star, the star moves slightly. This movement shows up as a tiny shift in the star's light, a Doppler effect that can be measured with precise spectrographs. LHS 3154b's gravitational pull is strong enough to make its tiny star wobble noticeably. That's how we know it's there. That's how we know it's massive. That's the smoking gun that says something big is lurking in this system. And yet, even knowing it's there, we still can't explain it. I want to share a thought experiment with you. Imagine you're an astronomer on a planet orbiting LHS 3154b's neighbor. You're studying your own solar system, trying to understand how your world formed. You look at your tiny red dwarf sun. You calculate the mass of the protoplanetary disk it should have had. You develop models of planetary formation based on these calculations. And then you look outward. You see a massive planet orbiting a star just like yours. A planet that your models say is impossible. What do you conclude? Do you assume your models are wrong? Do you search for exotic explanations? Or do you simply accept that the universe is stranger than you ever realized? This is the position we find ourselves in now. We are the astronomers staring at an impossibility, trying to make sense of a cosmos that refuses to play by our rules. And honestly, I think that's beautiful. There's a tendency in science, and in human thinking generally, to seek closure. We want answers. We want explanations. We want to tie everything up in a neat package and say, there, we understand now. But nature doesn't owe us simplicity. Nature doesn't owe us comprehensibility. The universe is not obligated to make sense to human minds that evolved on a single small planet over a few 100,000 years. Maybe the true lesson of LHS 3154b is humility. We've been exploring the cosmos for barely a century with any kind of precision. Before that, for millennia, we thought the Earth was the center of everything. We thought the stars were divine lights or holes in a celestial sphere. We thought the sun revolved around us. Each generation believes it has finally figured things out. And each generation is eventually proven wrong, or at least incomplete. I suspect we're no different. Our descendants will look back at our models of planetary formation the way we look back at the geocentric model. They'll understand why we believed what we believed, given the evidence we had. But they'll also know how much we got wrong. LHS 3154b might be one of the first cracks in our current edifice. The first clear sign that something fundamental is missing from our understanding. Or it might be an outlier, a cosmic fluke, a 1 in a billion event that doesn't represent anything general at all. We don't know yet. That's the honest answer. We simply don't know. But here's what I do know. In the next decade, new telescopes will come online that will revolutionize our understanding of exoplanets. The James Webb Space Telescope, already operational, is providing unprecedented detail about planetary atmospheres and compositions. Future missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Plato mission will find thousands more planets, many of them around stars we've barely studied. As our sample size grows, patterns will emerge. We'll see whether LHS 3154b is an exception or a harbinger. We'll find other massive planets around tiny stars, or we won't. The data will guide us toward new theories or validate old ones. That's the beauty of science. It's self-correcting. Given enough time and enough evidence, the truth eventually emerges. But in the meantime, we get to sit with the mystery. I know that some people find mysteries frustrating. They want answers now. They want certainty. They want to know that the universe makes sense. But I've come to see mysteries as gifts. They're invitations to wonder. They're reminders that reality is vaster and stranger than anything we've imagined. They're proof that the adventure of discovery is nowhere near over. LHS 3154b is a mystery. A beautiful, confounding, impossible mystery. And somewhere out there, 51 light-years away, it's orbiting its dim red sun right now. A world that breaks the rules. Planet that shouldn't exist. But it does. What does that tell us about what else might be possible? What other rules might the universe be breaking right now, beyond our ability to detect? What other impossibilities are waiting in the darkness between stars? I think about the early astronomers, the ones who first realized that the points of light in the sky were other suns. They couldn't have imagined exoplanets. They couldn't have conceived of hot Jupiters or super-Earths or water worlds. The idea that other stars might have their own planetary systems was purely speculative, even fantastical. And now we know that planets are everywhere. Almost every star we study has them. The galaxy is teeming with worlds. Trillions of them. Countless variations on the theme of planetary existence. What will we discover in another 100 years? Another 1,000? I suspect our descendants will find things that make LHS 3154b look mundane. They'll find planets that defy not just our formation models, but our very conception of what a planet can be. They'll find worlds where life has taken forms we can't imagine. They'll find cosmic structures and systems that we lack the concepts to even describe today. And they'll look back at us, at our primitive telescopes and our tentative theories, and they'll smile. They'll appreciate that we were doing our best with what we had. They'll honor the questions we asked, even if they've long since found the answers. That's the legacy of discovery. Each generation stands on the shoulders of the last, reaching a little higher, seeing a little further. LHS 3154b is a stepping stone. A waypoint on a journey that began when the first human looked up at the night sky and wondered what those lights might be. We don't know where that journey ends. Maybe it doesn't end at all. Maybe the universe is infinite in its mysteries, and the process of discovery goes on forever. I hope so, because if we ever reach a point where there's nothing left to find, nothing left to wonder at, nothing left to surprise us, then something essential will have been lost. The universe gave us LHS 3154b. It gave us a planet that shouldn't exist. A puzzle with no solution, at least for now. And in doing so, it gave us a gift far more valuable than any answer. It gave us a reason to keep looking. So here's my question for you. If our most fundamental models can produce planets like LHS 3154b, what else might be out there waiting in the darkness? What other rules might be broken? What other impossibilities might be orbiting distant stars right now, challenging everything we think we know? What do you think exists out there that we haven't even thought to look for yet?